So today we will be learning theorems on probability. So the first theorem is probability of the impossible event is 0. So how will you write probability of an impossible event in terms of an equation? Yes, probability of an impossible event. See, an impossible event, I'm representing it as phi. Okay, so this simple as phi. So the probability of an impossible event is 0. So we will have to prove that the probability of the impossible event is equal to 0. For that, let's see how we'll prove. Now, an impossible event contains no sample. Okay, contains no sample point. Right, I hope all of you know that. And hence the sure event, what is the sure event will be? The sure event will be S, that is the sample space. This is something that we have learned, right? And the null event, now how will you represent the null event? Yes, as I said earlier, null event or the impossible event, or you can just write it like this. Okay, and the null event phi are mutually exclusive. So what does this mean? The intersection of the null event and the sample space, that is the sure event, is equal to what? 0. Now what about the union? The union of this two, that is the null event and the sample space, that is the sure event, is equal to S. So what will be the probability of, I'm going to consider this part, what will be the probability of phi union, or the null event union the sure event? By using the additive property of probability, or by using the axiom that we have learned in the axiomatic definition, how can you write this as probability of phi plus probability of S is equal to probability of S, right? Yes. Now this implies, what does this implies? Probability of phi is equal to probability of S minus probability of S, which is equal to what? 0. Hence we have proved the first theorem. Now let's have a look at the second theorem. The probability of the complementary event of A, that is A complement, the probability of the complementary event A complement of A is given by probability of A complement is equal to 1 minus probability of A. Now we know that A and A complement both are mutually disjoint, right? Or both are mutually disjoint events. Then what is A union A complement? See, if this is the sample space, if this is the event A, this is the event A, then what is A complement? Right. So what is A complement union A? A complement, what do you mean by A complement? Those elements which are not in A, right? So what is the union of A complement and A? S, right? So A union A complement is equal to S. Now by taking probability, what will you get? Let's have a look. Probability of A plus probability of A complement is equal to probability of S. And what is probability of S? From the axiomatic definition of probability, you know that what is probability of S from axiomatic definition. If you have learned the axiomatic definition and the three axioms, it is said that probability of S is equal to 1. That is a sure event. So probability of A plus probability of A complement is equal to 1. Then what is probability of A complement? Is equal to 1 minus probability of A. So just check whether we have got our theorem part proved. Yes. Okay. Now let's have a look at the third theorem. Probability of an event lies between 0 and 1. Now let A be the event. And what is probability of, what does the theorem states? Probability of an event lies between 0 and 1. So that means we have to prove that 0 less than or equal to P of A is less than or equal to 1. So this I'm going to give it to you as an exercise. Please do come up with the proof. Okay, so moving on to the fourth theorem. Fourth theorem is nothing but for any two events A and B, it is said that probability of A complement intersection B is equal to probability of B minus probability of AB. Similarly, you will have to prove another statement, that is probability of, this is B complement. Probability of A intersection B complement is equal to probability of A minus probability of AB. Okay, so these are the two things that we have to prove. Now let there be two events like A and B. Okay, now this is the intersection of A and B. I hope you all know all these basic things. Now what about this area? What is this area? This is A and the part and this is A and yes, B complement, right? So the intersection of A and B complement. Now what about this area? B and B intersection A complement. Okay, fine. So in order to prove this first equation, that is probability of first theorem, probability of A complement B is equal to probability of B minus probability of AB, we are going to consider the event B. Now what is the event B by connecting all these things? What I have just written over here, what is B? B is nothing but, what is B? B is A intersection B, A intersection B union B intersection A complement. Will you agree with that? What is B? See, what is B? B is nothing but A intersection, that is this part, union B intersection A complement. So how will you write this, or how will you break this down? Now if you give probability to this equation star, you get what? Probability of B is equal to probability of A intersection B plus probability of A complement B. Now we know that How did you get this one? Yeah, by from this Venn diagram. And you know that here AB, that is A intersection B, and A complement B are disjoint sets or disjoint event. You can say that it is disjoint. Okay, so that is how you write B is equal to the star. That is how you got the star equation, and you applied probability. Okay, and from the from the axiomatic definition of probability, you can write the star like this, and then you get probability of B is equal to probability of AB plus probability of A complement B, which implies probability of A complement B is equal to probability of B minus probability of AB. Now similarly you can prove probability of AB complement is equal to probability of A minus probability of AB. So this is a homework. Please do it by yourself. Okay, now let's move on to the fifth theorem. Now in the fifth theorem, it is said that if B is a subset of A, then probability of AB complement is equal to probability of A minus probability of B. That is the first thing that you have to prove. Second thing you have to prove is that probability of B is a quantity which is less than or equal to probability of A. So it is said that B is a subset of A. So let this part be A, and since we have a condition like this, let this part be B. Okay, so this green is A and a subset of that is B. Now what is this part, the shaded region? So I'm shading this. What is this shaded region? This shaded region is nothing but shaded region is definitely A, right? Definitely A intersection. Is it B? No. So B complement. So it is A intersection B complement. Now that's all about the picture. Now let's see that now is B and AB complement, is B and AB complement mutually disjoint? Yes, it is. B and AB complement is mutually disjoint, or they are disjoint events. Therefore you can write this as what? A is equal to, now the whole of this is A, right? So A is equal to B union AB complement. I hope this is fine with you. Applying probability, the axiomatic definition, you get probability of A is equal to probability of B plus probability of A B complement, right? Which implies probability of AB complement is equal to probability of A minus probability of B. So the first part is proved. Now for the second part, we know that probability of AB complement, okay, probability, that is any measure of probability is definitely greater than 0. It has a limit, right, from 0 to 1. So it is definitely greater than 0, which implies that what is probability of AB complement? From the first result we know that it is probability of A minus probability of B. So since probability of AB complement is greater than or equal to 0, we can also state that probability of A minus probability of B is also greater than or equal to 0. That implies probability of B is less than or equal to probability of A. I hope this is also understood. We will move on to the next theorem. Next theorem is a very important theorem, and that is called as the addition theorem of probability. Now here I'm only considering the two event in this right now I'm only considering two events. So let A and B be any two events defined on the sample space S of a random experiment such that their probabilities exist. The probability of occurrence of at least one of the event is given by probability of A or B is equal to probability of A plus B, which is equal to probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B, where A intersection B is the event of simultaneous occurrence of both events A and B. If the events A and B are mutually exclusive, that is, if the intersection is something like this, if it is a null set over here, then, and if probability of the null set is 0, then you can write the same addition theorem as probability of A union B is equal to probability of A plus probability of B. So this is the statement of addition theorem. Next we will move on to the proof of the addition theorem. Okay. Now for the proof, I'm going to first consider the Venn diagram. Okay, so this is A, this blue part is A, and this part somewhat peach or beige color, whatever it is, that is B. Now this part, the intersection part, as you all know, it is A intersection B, and then this part, that is what I'm drawing right now, is A intersection B complement, and similarly this one is A complement intersection B. Okay, this part. Okay, fine. Now you just consider for the for proving this theorem, you have to consider A union B. So consider A union B. Now what is A union B? A union B is full of A. If you take full of A, right, so I'm going to write this as full of A, and what is the remaining? A union B. So some part of B is inside this structure. Now here the remaining, that is A complement intersection B, that should be included. So A union A complement intersection B. So this can be A union B can be written like this. I hope you have got the idea how I wrote this. Therefore, if you apply probability of A union B is equal to probability of A union probability of A intersection B. And we have to take into consideration one more point, whether there is any intersection term lying between these two, A and A complement intersection B. So let's have a look. Since A intersection A complement intersection B, what is the answer for this? Just have a look. A intersection A complement intersection B. Is there any common elements for these two sets? No, right? So it is a null set, so I give it as 5, okay, or 0. Okay, now what I'm going to do is I'm going to mark this as probability of A plus probability of A complement intersection B. This is also fine, right? So this I'm going to mark it as 1. Now the second part of proving this theorem is that we are going to consider B. Okay, now what is B? B is nothing but A intersection B, okay, A intersection B union A complement intersection B, A complement intersection B. It is the union of A intersection B and A complement intersection B. So how can I write this in terms of probability? P of B is equal to P of A intersection B plus P of A complement intersection B. Here also we have to take into consideration what is A intersection B intersection A complement intersection B. Just see the figure or the image. A intersection B intersection A intersection B complement. Okay, is there any common element between this area and this area? No. So this is again phi, or it is 0. Now this I'm going to write it in a form of probability of A complement intersection B is equal to probability of B minus probability of AB. I hope this is fine. And this I'm going to give it as equation number 2. And what I'm going to do is substitute 2 in 1. So when I substitute 2 in 1, what I get is probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So hence the addition theorem for two events is proved.